Here we will be able to explore the workings of the series RLC AC circuit using a simulation. In the simulation presented next, you will see on the left hand side the actual circuit, and the values of the current through the circuit and the behavior of the current will be indicated by an arrow. On the right hand side will be the behavior of the phases. All of the phases that are relevant here, the ones related to the resistance, inductance, and capacitance, all will be shown. On the bottom will be a set of values for the R, L, and C, which we will be able to toggle through and alter the behavior of the circuit. So here is the simulation. Currently the simulation is off. I have stopped it at the point where the green arrow here is lined up along the x-axis. So that is our starting point. The green arrow represents the current in the circuit, and since it's lined up with the x-axis, the current in the circuit, as shown by the green arrows here, has the maximum value. We have chosen to select the display of all of the quantities, the resistance, inductor, and capacitor, as well as the net voltages. So let's go ahead and select only the resistor and get the simulation started. Now, of course, the voltage across the resistor is in phase with the current, so that's shown by the yellow arrow here, and the voltage has the value I max times R. And as we start the clock, the two phases rotate in the anti-clockwise direction, and you can see what's happening to the current. So the current through the circuit goes up and down, and it goes through zero and also reverses the direction. So this means the generator is producing a voltage at 60 Hertz. It goes up and down as we are familiar with the working of a generator. And corresponding to that is the behavior of the current in the circuit. It also goes up and down with a progressive change in the direction of the current, and one can understand that behavior in the phasor diagram itself by looking at the projection of the current as shown by the green arrow. So right now it hits zero, the projection is negative maximum, here it's positive maximum, it's zero, negative maximum, positive maximum, and so on. Now let's turn on the other phases. So let's look at the inductor first. And you can see that the inductor, the reactance that I have chosen is very small, so that's why the arrow is real tiny here. So let's stop it and go ahead and use a larger inductor. So from 90 millihenries, we're going to go to as large as possible, 200 millihenries or so, and you can see that the length of this arrow increased. And of course, the direction of this arrow is such that it's leading the voltage by 90 degrees and reading the current rather by 90 degrees, since we know that the voltage across the inductor leads the current by 90 degrees. Similarly, if I turn on the capacitor, you can see another pair of arrows pop up. So we have the voltage across the capacitor given by this pinkish arrow is I max times the capacitive reactance, and since the capacitor that I have chosen is really small, it's towards the small end of the range, the capacitive voltage is large. If I increase the value of the capacitor, I'm going to decrease the contribution from the capacitor. Now, at this point, so this would be the behavior of the circuit as time progresses, and the current, of course, the magnitude of the current will depend upon the individual values that we have chosen. So let's see if we can alter that. So suppose I increase the resistance to a larger value, one expect the current to decrease. Let's see if that happens. So clearly the magnitude of that green arrow decreases as I increase the resistance. Now let's go ahead and see if it's possible to get a resonance. For that I will have to increase the value of the blue arrow. I have reached the maximum value of the inductor that's allowed in this simulation. So the only way I can do this is to decrease the value of the increase rather the value of the capacitance. So if I increase the capacitance to a point where these two arrows are equal, that is my resonance condition. At that point, you will also notice that the phase angle gets closer to 0. So let me put the net phasor back there, go back to a value where there is no resonance, and you can see that the voltage phasor has an angle with the current, and this angle is of course the phase angle we compute as using the cosine phi equals r divided by z relation. And if I increase the capacitance, I go closer to the resonance condition, and the phase angle simultaneously becomes equal to 0.